Hi, my name's Andrew McLaren, and I want to help you with problems involving equilibrium or K values, sometimes called K equilibrium. Now, this is going to be something that oftentimes is involving gases or something else that's competing over space. And it's really important to, whenever you're writing out these types of problems, just give yourself a reminder that this is product over reactant. And so when you have big numbers, that's favoring the products, aka we're going to have more products and more reactants if this value is like bigger than 1. Now, if this value is less than 1, then it's a small K equilibrium value, and this is favoring the reactants. This is really important to at least write out what I've got here whenever you're doing problems in K equilibrium, because it's easy to flip and accidentally do the reactants over the products. And you're going to get incorrect answers if you're doing that. So if we're looking at this expression, this K equilibrium, you're going to be putting the coefficients, the numbers that are out front, in here, because you can think of this as some sort of reaction where we've got the products over the reactants. And so our product here is the NBr3, but you might as well think of that as two different products. So you're going to have to multiply those together, just like you are going to have to multiply two different reactants, the N2 and the Br2. So if you've got the N2, you've got one of those, and you've got actually 3 of these Br2s. So I'm just going to write it out like so, showing that we really have 4 different reactants coming together. So it's kind of like you're multiplying 4 sets of numbers. But we usually write this out using squares or cube powers in the expression just to condense this down. But we have 2 different products here. So as the amount of product comes up, you need to multiply 2 numbers together. That's why it's being squared. And we've got our product on the top, our reactant on the bottom. Most common mistake is to flip these. As you can see, they tend to give that mistake as an option. Like what we're seeing in 1 there. That is not correct. We actually have number 3 being our answer here. So C would be correct. We've got a couple of other problems that I'm going to go over today, just a little preview. You'll be able to skip ahead if you're like, okay, I have that problem down. But it's good to have some numbers when we're looking at this, because we'll talk about the general relationship, but it just can help to actually look at numbers while we're discussing this. So a really common thing for them to do is have you look at some K expression where you've changed the number of coefficients in there. So we've got this reaction with 2, 1, and 3 compared to 6, 3, and 9. And I'm going to just pretend that you've got 2 atmospheres for each, and just like see what the math would look like. So if we had this K expression here, for the normal thing, you've got K and you've got the products over reactants. I'm going to call this K1 for this first reaction. Now its product is C, which is going to be cubed. And we've got A, which is going to be squared. And you've got B, which is just up to the first power. And if we had 2 going inside for all of these numbers, you can see that this is going to be bigger than 1, because you got 2 up to the third power. And then actually, well, actually, no, this doesn't, this is actually equal to 1 when we do this. So we've got then 2 up to that second power, and B up to that first power. So this K expression is equal to 1. So if we are looking at this K2, it actually is, unfortunately, when you have 1 here, the math is kind of interesting, but it's worth highlighting. So its products over reactants, if you still had these numbers, but now instead of being up to the third, second, and first power, C is now going to be up to that ninth power. And then A is going to be up to the sixth power, and B is up to the third power. So interestingly enough, when these all are exactly the same numbers with this particular K expression, it just kind of cancels out. So you've got 2 up to that ninth power on the bottom, and 2 up to the ninth power on the top as well, because when you have these same base numbers, you just multiply or add up the exponents. So this is also equal to 1. But if you cube 1, like if you put something up like like 1 up to the third power or negative 1 third power, if it's 1, it still is 1. So our math, just in this particular case, it happens to work out to being the same. But let's pretend that we've changed b to actually being equal to 4. So if we were to do that with b is equal to 4, now you don't have something that's equal to 1. Now you've got 2 up to that third power, 2 up to the second power, and 4 up to the first power. So this is actually 1/2. If we were saying K equilibrium is with those numbers. So if we were to also look at 2 up to the ninth power, 2 up to the sixth power, and then 4 up to the third power, you can go ahead and do that. This is actually 2 up to the second power and then cubed. So this is no longer 1/2. It's going to be 1 over, I believe, 8. So we can go ahead and get that in the calculator just to prove that. But if you can kind of see, whatever number you're putting in here is going to be affected by the coefficients in a way where it's like, okay, just take the K expression and put it up to that exponent that you multiply these base coefficients by. So if we've like 2 up to the ninth power is that, and then we've got, let's just say it's got 512 on top, 2 up to the sixth power, 64 times 4 up to the third power, 64. And if we've got 64 times 64, that's a pretty big number. So we've got 512 divided by, what was it? 40. Yeah, we've got 1/8 right there. So you can kind of see how you need to take K and put it up to the relevant exponents to change this stuff. And so if we have 1/2 and we put it up to the third power, you get 1/8. So if we get 0.5 or 1/2, you put that up to the third power, you get 1/8. So because we multiplied the coefficients by 3, going from here to there, you need to bring this up to the third power when you're changing a K expression with a new reaction with new coefficients. Even though it's the same balance of atoms, like they still are competing for space and still getting the same amount of space here. But the expression, the mathematical expression, is going to be a bit more extreme if you've got more coefficients, because more numbers are being combined. So if you've got more big numbers in there, it should kind of make it more drastically large or small number in the K expression. When we're talking about K equilibrium, this is essentially saying how much space do these things get. If this is talking about them favoring products or reactants, it's really how much space or the piece of the pie that it gets. So if someone's taking more of the pie, then they're favored, is what I like to think of it as. Now that means that when we're talking about ions in a solution, they are competing over this large area. There's like this large area that they are fighting over. And you might have a little bit of solid down in the bottom here, but that solid, if you change how much solid is present, that's not going to affect the K equilibrium. So this number isn't included. And if you look at how we're writing these things with the brackets, that actually is referring to concentration. So if we're talking about a K equilibrium with ions, it's kind of implied with how we write it that you're just not writing in the this solid right here. This solid means that it's not included in its K equilibrium. So for its products over reactants, we just are going to talk about the relevant amount of these products that are present. We've got some magnesium, 2 plus, but when we do concentration of ions, we have those little bracket things to show those numbers there. And we do have 2 of these chlorines, so you could write out chlorine times chlorine, but we might as well just do that, the exponent. Because the reactant, we can't really include that. You can think of that just being all over 1, so you can just write the multiplication of the 2 things together. So we have something that looks like answer B here. If we did have just 1 chlorine in the reaction, then C would be correct, but we gotta be careful. And as you can see, they're trying to throw you off with the inverted thing with A and D there. Be careful. Sometimes they're gonna give you wrong answers that, like both options, like they're close, they're both wrong. Multiple choice, man. Ins and out of it. If we're talking about this reaction here, you can see in a similar regard to what we talked about in the last problem, solids, they don't really compete over space. So we're just interested in the CO2 and where that goes in this. So if we've got the products over reactants, there's only one number that's relevant. It's the amount of CO2. And there's just one of them, so it's just all over 1. So you can say that this is just that pressure of the CO2 by itself that we're going to be talking about here. You could have like 1 molecule of the calcium carbonate or 1,000,000 molecules of the calcium carbonate. Does not matter. It's not really competing over space. We're really saying like CO2 gets this amount of pressure. And in this problem, because we just have one thing here, I'm going to call this K1. If the expression is 5.0, that's like, that is the pressure. It's 5.01 atmospheres of CO2. And that is going to be for this forward reaction here. Now, if we're talking about the reverse reaction, I'm going to call this K2. This is going to be for its products over reactants, which is the opposite of the reaction above. So if we're talking about CO2 plus calcium oxide reacting to form this calcium carbonate, now this number is a reactant, so it needs to be down here in the K expression where it's appropriate. So we've now got 1 over 5.01 in this particular problem for the atmospheres of CO2. So the equilibrium constant is just the inverse. So 1 divided by 5.01, it's about 0.2, yeah. And we probably would round this up to being 0.20 for its K equilibrium. This is a pretty quick one. If we've got a number that is bigger than 1, this is kind of big relative to things that are less than 1. So we're saying that the K expression, the products over reactants, it seems to be favoring the products a bit more. And they're close. So I wouldn't say there's many more. Like there's a bit more product than reactant, but it's not like a ton. Like these things can be like 10 up to the 3rd power, 4th power, 5th power, very, very normal, or 10 up to the negative 5th power. All of those are normal values. So this is pretty balanced in terms of orders of magnitude. It's not like it's 10 times bigger or 100 times bigger than that product to reactant. So if we're combining 2 K equilibriums like this, it seems a little bit tricky at first, but you just have to think about the product reactant relationship in general. So if we've got a K1, let's say we're talking about K1, which is going to be for this guy right here, it is going to be its products over its reactants, which happens to be the B over A number. And when we get that, it's going to be 8.5 We don't know the exact concentrations for these things, but we don't really need to. For the K2, right here, the A to C number, we've got its products over its reactants, which is going to be C over A. So I'm going to call this product 2 reactant 2, product 1, reactant 1. So if you want to now get this third reaction, let's call that K3, it will be its product over its reactant, which in this case is going to be B over C. If you do a little bit of math, you can see like if I want to get B over C, I'm going to need to flip this K2. So I'm going to be thinking about not K2, but what I'm going to call K4. Which is the inverse. So if we're talking about K4, this is for the reaction of going from C to A, and it's going to be the inverse of 2, so it's going to be 1/2. As opposed to this number, which was 2 over 1. So the top number becomes the bottom number, essentially. And you could think about this 8 as 8.55 all over 1 as well, in a similar regard. But we don't have to flip or invert the K1 for this combining these two. So K4, whatever that number is actually going to be having a value when you put those two together of 1/2. You can see also with just like the math here, if you want B over C, you're gonna need B over something times C under something else. So we want to have like what we're saying right here, this is going to be its product over its reactant. So we're getting the A over C here. So we've got the A over C, and then we've got the B over A number right here. And while we don't know the exact numbers, you can kind of see that we have a value of 8.55 for that K1 expression. I'm multiplying that by a value of 1/2 for this other reaction. So we had to invert that K expression and then multiply them together to get this new K equilibrium. So yeah, it's going to be like around 4 something. So yeah, 4.275 for this K equilibrium. That's appropriate for the amount of product of reactant. In other words, this was favoring product, and this was going to also favor their product, but you need to flip it because now we're thinking of this as favoring the reactant, but it doesn't favor the reactant enough to outweigh the other bigger K expression number. So in general, this new final thing is going to be favoring the products because it is just pushing forward more than this other thing is pushing backwards, is one way to think about it. For this problem right above, we've got a K expression that is given for a reaction written as A forming 2 B's. So it is going to be its products over reactants. We've got B up to that second power and A up to that first power. I always write this out. I cannot emphasize that enough. But now we're considering doubling up the reaction. So this new products over reactant, we still have the products in top and reactants in bottom, and it's actually the same numbers, but whatever those numbers are, they're up to even bigger exponents. So if this gave us a value that is less than 1, we can say that it's like A is favored. And we're still seeing that in the case here, but the degree that it's being favored is going to be even more. It's just like you're putting up to a bigger exponent. So to get what we're going to call K2 compared to K1, you need to put this thing up to the second power, because you just have more of these numbers being combined. You can see that this is actually, if you were to take B up to the second power and A up to the first power, and then multiply that with another one, you're going to get that B up to that fourth power over A up to that second power. Now each one of these has a value of 0.780, and so you're kind of just squaring it right there. That's another way of looking at this with math. So it's just going up to that second power. So if we take the 0.078 and we raise that up to the second power, or just multiply it twice, we get this 0.006 number, which makes sense. It's getting a representation that's still favoring the thing that was favored, but when you multiply the numbers out, you need to multiply them out twice, essentially, compared to what you were doing beforehand. So when you're looking at this new reaction, it's not like it's changing the amount of stuff that is stable compared to the other stuff that is stable. Like, they still are getting the same amount of space. It's just the math of the expression needs to be a bit different. So this is when things get a little bit tricky for people, but if you just slow it down, it should be okay. We've got this reaction right here, and when we look at it, we've got a K expression that is favoring the reactants. So for this product over reactant expression, because it's coming out as less than 1, reactants are favored compared to the products. I'm going to call that K1. And then we've got this other reaction. Now you can see it's been flipped, so the reactants are now the products, and we're changing the coefficients. So what I'd recommend we do is just do this one step at a time. So if we want to think about K2, we can go ahead and flip this. So if we want to think about the product over reactants, but for F2 combining with H2 to form HF. Now, because the reactants and products are kind of on opposite sides, we need to do the inverse of that number. So it's now 1 over that 0.460. We can get that in the calculator. Or you could put that to the -1 power. And then going from there, K3 is, we're going to take that and make these go up to like the half power. So you've got 1/2 of the F2 and 1/2 of the H2 forming 1 of the HF. So we are having not like this the exact same number as that 2.17, but we're still favoring products. But the math works out a little bit differently. So here we're like saying, yay, the products are favored, reactants are not favored, and we'll still see that in this K3 expression, but how the numbers would be combined, you're not going to get the same K expression because you're multiplying by a different number of them. So here we're seeing that like products are being favored, reactants are not being favored, but we need to divide all the coefficients by 1/2, so this is going up to like that half power. So you're going to have that 2.17, and then you're going to bring that up to like a 0.5 or 1/2 power. 1.477. And you can think about, if I were to multiply everything by 2, it's going to be raised up to that second power. So we can double check that by taking that number and raising it up to the second power. It does look like we are getting that K2 when we do that. So that makes me pretty confident that we've done our math correctly here. This problem's not too bad. We're just kind of plugging things in. make sure you always write out products over reactants here. Just very common for people to mess up that when they start getting to these problems. We're like, okay, I think I'm getting like the hard stuff, and then they start messing up the easy steps. This is going to be squared because it's got 2, but each one of these do not have any coefficients in front of them, so we're just multiplying them out. And they've given us partial pressures at equilibrium, so we need to just multiply that out. 1.9 atmospheres of the HI. And I would write out the substance and units here just to make sure that you're putting them in the right spot, because that's pretty easy to mess up. We've got that guy written in there. And then we've got the H2 and the I2. Luckily, these numbers, they don't really matter where you do them because they are the same coefficient for both. But I'm going to write in the units just to have good practices for other problems where those might be up to, like, maybe this is up to 2 or 3 or something like that. So you would just need to be careful which part you put it in, because you'll get a different number otherwise. And then actually this is the H2 number, and the other one was the I2 number. The English language, man, sometimes it can just be a little bit confusing, because the H2 is that 7.9 and the I2 is that 1.3 number, is what I'm seeing. So we just multiply those out appropriately and divide by that 1.9 squared, and we should get something that's appropriate. Now, what I would recommend is doing the top and the bottom numbers and then condensing that down. So I would get that as 18.17 all over 1.9 squared. So that's getting me a 3.61, which sounds about right, given like 2 squared would be 4. And we've got now the 18.17 divided by 3.61. Yeah, writing out the top and bottom numbers separately just makes you able to see if your number actually makes sense when you get to the end, and be able to be like, wait, where did that come from? Do I really have more product or reactant when we're thinking about this in terms of this K expression? It does seem to be the case here that we're favoring the product. But it can be a little bit tricky with these exponents. You gotta be careful, because you can't just be like, oh, these are bigger numbers, those are smaller numbers, because maybe this was up to like the 5th power in the bottom, and that would change the K expression, because that would be a bunch of products in small amounts, but that's still a bunch of products. So yeah, you gotta be careful on those, how you're thinking about, do I have more of this stuff or less of that stuff? This is kind of similar in the big picture thinking of this K equilibrium to the last problem. But if we're talking about product over reactant here, we can set this up having our H2 times the amount of I2 all over the HI being squared, due to there being the 2 right there. And they've given us the overall expression for K. That is something that is provided as 7.21. So we've got 7.21 being equal to some amounts of these things. We've got 1.20 molar of the H2 for 1. And for that second one, we've got that 1.70 molar I2. And this is why I write in my substance, and I really recommend just getting the general expression written out above, so you can make sure you're putting things in the correct spot, because we do want to make sure the product is over the reactant. And then we have some mystery number here for the HI that we're solving for that would be squared. So I'm going to double check this by plugging it back in, but we've got some math to do. If we got that 1.20 times the 1.70, the top of this expression would be 2.07, I believe, or 2.04, sorry, close. all over this mystery number squared. If you know your math, we can just kind of rearrange this and say that the question mark, this hi squared, is equal to 2.04 divided by that 7.21. And that was equal to 0.2829, but we're going to square root that. So this mystery number, this concentration of the HI would have to be square root of that. So 0.5319, I believe. And we can double check that by plugging it back in. So we can take our number and be like, does that actually work here? And if we get 0.5319, we square that. Yeah, that's going to be in the bottom. And we can take our number right here and see that that's equal to what we've got there, because that was the question mark squared. So if we've got 2.04 divided by 0.2829, that is giving us our original K expression. So it plugs back in nicely. Yay. So this is a kind of a weird thing. I just generally think of K as products over reactant. But if you're technically looking at concentration versus pressure, because the units are different, the exact calculated value can be different. So Kp and Kc, they're related through this RT change in N relationship. But I like how in this expression, how they write it, because they're showing how each individual pressure is related to the gas law right here. So you've got PV equals nRT kind of being put together in this. So you can kind of see that. So each one of these pressures is going to have some mathematical expression there. N over V is concentration. So this N over V component right there, the N over V is, you can think of that as moles over liters, which is what we're talking about when we're doing the big M. So we have a bunch of RTs up to like the change in moles, because you've got C, D, A, and B. If you remember your exponent rules, if you have like 10 up to the third and 10 up to the second, this is 10 up to the 3 minus 2. Or if you have 10 up to the fifth power times 10 up to the fourth power, this would be 10 up to the 5 plus 4. So this change in N is looking at the C and D, A and B relationship. So you've got C plus D minus the A plus B. In other words, how have we changed the moles? Is there more moles of the product, or is there more moles of our reactant? And that should change our overall relationship. If anything up to an exponent value of 1 is, that's going to change things a little bit, but anything up to the value of 0, it's the same number. So it doesn't matter if you have like 1,000, if you put that up to the 0 power, you got 0. It doesn't matter if you've got 562 up to the 0 power, that is 0. In other words, you've got 0 sets of the number being multiplied. I like to think of this as if you had 10 up to the third power divided by 10 up to the third power, this is 10 up to 3 minus 3. So it kind of shows that this ends up canceling out. Oh, actually, sorry. No, this ends up being a value of of 1. That's how it works. So this whole expression's value is 1 if the change in n, if we don't have any change in the number of moles of gas. So we need to look at these problems and say, do they change the number of moles of gas? If not, then the Kp is equal to the Kc. So I'm seeing 2 to 4, that's changing. 2 to 1, that's changing. 3 to 3, that actually looks like that works. So it's not changing the number of moles. And I'm seeing that as well here. Actually, no, it's just D, because we're really just talking about gases. Yeah, the solids do not get included here, so we're having a 2 to 1 ratio for C, where we've got 1 mole of gas in the product and 2 in the reactant. So D is the only answer that is going to work here.